So what were we talking about? We were talking about LU factorization, which is traditionally the topic that this kind of class starts with. And notice that we're getting into it about halfway into the semester, and that's because we now, well, first of all, it means that those who have strong linear algebra backgrounds get to see something new up front, and that sort of creates a little bit more excitement. Of course, for those who had a weak linear algebra background, that probably created some anxiety. And hopefully now things will sort of relax a little bit. We're going to talk a little bit more about the LU factorization today. What I would like to do is look at some other algorithms for LU factorization that are out there, and each of them sort of has their place. And I'm going to talk about sort of something that you won't see in any class other than mine, which is I'm going to talk about how to formally derive these kinds of algorithms. I'm going to try to really link that to the proof by induction that crops up a lot when you do proofs about LU factorization. And then, if we have time, I'll talk a little bit about blocked algorithms, which are ways of achieving high performance in a portable fashion. Okay, so, and those are topics that we'll talk about a little bit today and a little bit on Tuesday. I may just let the schedule slip just a little bit. Okay, so let's get started. Let me bring up.
One last question about the exam.
Sure.
Are the questions on the exam the same type of questions you would have given us had the exam been in person?
I think they're epsilon harder,
Yep.
but not much harder. Okay?
Small epsilon.
It's a small epsilon.
Bounded.
I think there would have been some people who would have given this as an in-class exam, but they would have given it under the assumption that if you got 30%, you were doing great.
Okay.
Okay? I'd much rather give you the time to get to 90 to 100%. Okay? Think of it that way. Okay. So let's pop this up. This is something I put together. You took my programming for correctness course, right? Or was it my high performance? Not you, but
No.
Paul. Which one did you take? Oh, you took the 329C.
Yeah.
Never mind. Okay. So then you haven't seen this either. Okay. Okay, so let's put the screen down. And actually for this, I may just want to record my screen as well. Hold on. Let me get ready here. Okay, we'll see if we can get somewhere. Let's put the screen down. Okay, so here's the idea. We talked about LU factorization. And one way in which we can describe this is that you have a matrix. Let me double check, maybe I have another pen here. Hope so. Yes, I do. And as part of the computation, you've gotten through part of the matrix. And what is the state of the matrices at this point? The state of the matrices at this point is that this is done, and this is done. And this has been updated. Okay? And this is very much like Gaussian elimination, because when you do Gaussian elimination, at some point you say, and then you continue with the smaller subproblem. And here you have updated this matrix in such a way that you continue with the smaller subproblem. And to continue with the smaller subproblem, you repartition, you essentially take alpha 1, 1 and divide it into this part right here. And then you do this times that to update that. Okay? Now, a good chunk of you guys are computer science students, and a subset of you will have encountered the idea of a loop invariant. Can I see hands of who've encountered? Okay, it seems like it used to be that only students who got their undergraduate degrees here and at Cornell had been exposed to these, but these days they actually bring the term up in sort of the early programming courses instead. Now, what is the loop invariant? The loop invariant is the state of the variables at the top of the loop. Okay, so let's put the algorithm up here. That was the LU factorization algorithm that we came up with. And if you ask the question right after the while loop, what is the state of the matrix? It's this business of this quadrant is done, 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 and this quadrant has been partially updated. Okay? And then, so in the late 1960s, early 1970s, people were big into that one should formally derive algorithms hand in hand with their proof of correctness. And this, I've mentioned this before, and this is in part what Edgar Dijkstra got his Turing Award for, and he was a great proponent of this. This was called goal-oriented programming. And that was all very nice, but nobody managed to actually make it practical for any kind of applications, and therefore it was kind of a pie-in-the-sky kind of thing. And what people would do on occasion is actually prove after the fact, after you'd come up with the algorithm, how to then come up with this state called the loop invariant so that you could prove it correct. And what we're going to see is that we can actually do what Dijkstra wanted you to do, which is you state the problem of what it is that you want to compute. And from that, then you systematically derive the algorithm. Okay? Now, generations of numerical linear algebraists have lived very happily without ever seeing this lecture. So what you should do is kind of sit back and enjoy this, okay? So this is for your edification, or maybe it's for my edification, I'm not sure, all right? But this is really cool stuff. And what it really drives home is the link between loop-based algorithms and the principle of mathematical induction, proofs by mathematical induction. Okay, so here we go. And so what we did about 15 years ago is we discovered how to do exactly what Dijkstra wants us to do for linear algebra operations. And we made it then so systematic that one of my students, for a small part of his dissertation, automated the whole thing, so that everything that we're going to do by hand right now can actually be done by a program in Mathematica. And then, and that's pretty exciting because, you know, as computer scientists, we want to make things systematic to the point where they become automatic. And then we build entire libraries around this that actually have been proven correct, which actually were licensed to Microsoft, so this may be the only correct thing Microsoft ever invested in. No, I shouldn't say that about my sponsors. Gosh. They very generously sponsored this, and actually I think that for a while they had the most exciting group in scientific computing going until they killed it off. Okay, so here we go. So here's the idea. Let me just jump in. I'm going to show you how to derive one algorithm, okay? And this is how it all starts. It starts by stating what you want. You want a lower triangular matrix L, or unit lower triangular matrix L, and an upper triangular matrix U, such that A is equal to L times U. Okay? And what you've noticed is that we often want to simply overwrite the original matrix with the new matrix. And therefore, we're going to, now, this is the algorithm that is going to pop out. And you all have, of course, seen this template of how we express algorithms many times by now. So I don't need to explain this to you. But what you find out when you look at this, and what you look at almost every algorithm we'll talk about in this class, is that inherently you march through the matrix in a systematic way that exposes submatrices, sometimes quadrants, sometimes a left and a right matrix, sometimes a top and a bottom matrix. And then we somehow need to decide how to update some parts of those matrices in the current step. Okay, that's the theme. Now, what we want is we want to prove the algorithm correct. Okay? And what this requires is this notion of a loop invariant that tells you what the state of the matrix is. The idea being that if you can prove that you're maintaining that state every time through the loop, then you know that that state is true when you come out of the loop. And if then the fact that you got kicked out of the loop also tells you that you've swept through the entire matrix, then you know that you have hopefully computed, not hopefully, but hopefully you can prove that you've computed the right result. That's the idea behind all of this. So how do we do that? Oh, there's a busy slide. Okay. If you look very carefully only at the white parts, you will recognize the algorithm, except that we now also expose L and U along the way. Right? So ignore everything that's in the dark boxes or in the curly brackets. And there you have the algorithm. And then what is in the dark gray boxes represents the state of matrix A. It describes the state of matrix A at these different points in the loop. Okay? Now, if you think about how hopefully you have tried to write loops and reason about the correctness of your loops, hopefully you stare at your loop, you scratch your head really hard, and you sort of go, is in the variables at this point exactly what I would like for the variables to be in, at this point? And then you kind of reason through it. Okay? This simply formalizes that. We're using logic to express what actually is in the variables, and then hopefully going from one box to the next, we can reason that indeed what is supposed to be there is in there, and therefore we can argue that we actually have the correct algorithm. Okay? Now that's how you would prove an algorithm correct. And how does this fit in with proof by induction? Well, before you enter the loop, you're going to state what is a matrix A. That is your base case in your proof by induction. You're then going to say, let's assume that a certain state is true at the top of the loop. Let's prove that it's again true at the bottom of the loop when we've shifted through the matrix slightly. Okay? The assumption that it's true at the top of the loop is your inductive hypothesis. Proving that it's again true at the bottom of the loop is your inductive step. You can then invoke the principle of mathematical induction that tells you that then it must be true every time you go through the loop. Now, in mathematics, you would then say, then it's true for all n. The difference here is that it's for some n, you actually pop out of the loop because you've reached the end of the matrix. And therefore, after you come out of the loop, which would be right here, this condition that you're trying to maintain is still true. And if you can then say, the condition is true, but I have reached the end of the matrix, implies that I've computed what I wanted to compute, then you've proven your loop correct. Okay? Now, rather than teaching you how to do that, what I'm going to do is going to illustrate to you that you can turn it around. You can start by stating what it is that you want to compute. You can then come up with a state that you might want to maintain as part of the loop invariant. And then that is going to dictate exactly what the state must be at the different points in the loop. And that's then going to dictate exactly what must happen in the loop, so that not only do you come up with this proof of correctness that involves the assertions of what must be true where, but along the way you actually also come up with the algorithm that then makes all of those assertions true, so that you then have proven your algorithm correct. And all of a sudden, computer science is a lot like math. It's proved by induction. Okay? Which means everybody who's in computer science can just go take math courses now. No, obviously not, right? But it's kind of exciting. Okay, are we ready for that? Turns out to be remarkably simple. One of the reasons why in my group we particularly like this is because our goal is always to have high performance implementations. And high performance implementations often have to do with how you touch memory. And with this methodology, we can very systematically come up with all the algorithms that compute, for example, the LU factorization. And once you have all of the algorithms that compute a certain operation, you can then choose the one that matches the architecture on which you're trying to implement it best, and therefore you can get better performance. So we actually achieve better performance thanks to Dijkstra. Okay? Not that he could have cared less about that. Yeah. His statement always was, if you've proven your algorithm correct, there's no point in actually implementing it because you know it to be correct, right? Now, that's not because he really believed that, but that's because he tended to make extreme statements. I suffer from the same problem on occasion, so I apologize for that. So let's get into this. This is kind of cool. And what I will do is I'll have these slides. Hopefully, I'll post the slides. Hopefully, the video will actually turn out. We're getting a little low on batteries, so I'm not sure. We can always hope. And then we have some papers that I'll also put on the wiki page as enrichment. And then we even wrote a book about this that you can download for free. So if you are really into this, like we are, this is kind of cool. So let's start with a quote from Dijkstra himself. By the way, Dijkstra was not a Dutchman. He was a great Texan, because actually, you know, once he had achieved many of his great achievements, he was hired by our department. And I actually had an office next to his, which doesn't mean he ever talked to me. As a matter of fact, I think it was a good 7 or 8 years before he realized I too was Dutch. Okay? So, you know, there's no fame rubbing off on me here at all. But he does have these wonderful quotes. You really should go and look at Dijkstra quotes. He tended to give his lectures very carefully. He would write down what he was going to say, and as a result, there are these wonderful quotes from Dijkstra. And this one is, the only effective way to raise the confidence level of a program significantly is to give a convincing proof of its correctness, but one should not first make the program and then prove its correctness, because then the requirement... Anyway, you can read, right? You get the point. Well, that's a tall order, right? How many of you have hacked the program together and then you do a whole bunch of testing, and then you know a LAPAC, which is you know the most important package in this area, is generally considered to be correct because there's only a bug report once a month or so, okay? Which doesn't really give one a whole lot of confidence. By contrast, we had an entire library that has similar functionality, although a subset, which we developed over a matter of many years, where we derived the algorithms to be correct. As a result, we never really tested it. But at some point, the primary person who maintains this library, Field Van Zee, decided that he had made a very dramatic change at the low level of the library, and that therefore maybe it would be good to develop a test suite. So he developed a test suite. He spent several months on that, and of course, we did not test the test suite on the library. No, you create a test suite because the scientific test is to turn on the switch, run the tests, and see how well you did. So at the end of several months, he ran this against our library, which meant that for every matrix size, he ran 140,000 tests. Okay? You know how many bugs there were in our library? 2, which were easily fixed, and then for all matrix sizes, everything was just fine. Okay? That's the level of
now, you could say, well, that means he wasted several months of his life writing a test suite, but obviously this is useful anyway. But that's the level of confidence that you can have in your software if you approach programming like a computer scientist, systematic. Okay? I'm sorry, I kind of feel the need to impress upon those who are not in computer science that computer science truly is a science. As a matter of fact, I would claim it's the purest science because we try to make knowledge so systematic that it can be automated, and it's only in automating it that you can truly prove that you understand it. Okay? So that's me on my soapbox, and of course the irony is I don't even have a PhD in computer science, but let's not go there. Okay, so the concept we came up with was a worksheet. I should be able to hand you a worksheet, hand you an operation, and even if you don't know what that operation does, you should be able to go through a set number of steps and derive the algorithm, which then when you implement it should give you the correct answer the first time. Even though you don't really fully understand what it is that it is computing. Okay? That's the goal. So for this we developed a worksheet, and this is the worksheet. And this may be a little hard to see, but essentially you see a while loop there, right? Which is the while loop that has shown up in many of the algorithms as we expressed them in this class. Okay, and we're trying to come up with an annotated algorithm. Annotated means that we've inserted assertions about what should be correct at the various points. For this particular operation. So how do we start? Well, it'd be good to define what the input and what the output is. Okay? So what is the input? We're trying to write a routine that when you plug in A, you get back a matrix A that has been modified in that it's been overwritten by the lower and upper triangular parts. Well, the lower and the upper triangular matrices that are its factors. Okay? Now, notice that because we want to reason about it, and because we overwrite A, we need to have the concept of the original contents of A so we can reason. So we're going to introduce A hat as representing the original matrix A, so that when we reason about A, we're really saying what are the current contents of A. So when we start, A has its original contents in it. That's what the precondition tells you. And when we're done, we would like for A to have been overwritten with L below the diagonal and U on and above the diagonal. That's what that slash is supposed to indicate. Such that L times U is equal to the original contents of A. And notice that implicit here is the assumption that L is actually unit lower triangular and U is upper triangular. And obviously that should be part of the postcondition as well. But for conciseness, we're going to be a little bit sloppy with that. Okay, so there's some hidden assumptions along the way. And that's just to keep things manageable. Now obviously, the automated system that my student Paolo Biancanesi put together would be able to juggle all of these conditions. And therefore, in his system, they would be explicitly done. So what do you do with this? Well, you insert, this is a little hard to see, just notice that at the top there's something red and at the bottom there's something red. And if we home in on this, at the top we inserted that A has its original contents A hat, the precondition, and at the bottom we inserted the postcondition. Okay, so this just defines what it is that we're trying to compute. You with me? Let's go on. The next thing we're going to do is not what everybody else would do, which is slap down some algorithm and then try to scratch one's head and reason about whether it's correct. We're going to say up front, what might we want to maintain in the matrix A as we compute. Okay? So we are going to say, a priori, we're going to try to find the loop invariant. And that's the key ingredient that, in my humble opinion, nobody figured out back in the early 70s. How to a priori come up with these? Well, they did actually, but only for the simplest of examples. And I would like to claim that the reason why they could only do it for the simplest of examples is because they always express the algorithms with explicitly indexing, etc. And as a result, it was very hard to see the forest through the trees. Notice that what we do with our notation is it allows us to reason about regions as opposed to individual entries, and as a result, we don't get caught up in the little details of all of those things. I mean, how many homework problems have you done where you get caught up in the tiny little details of everything that's going on, and then when you see my solution, you go, oh, had I only thought about it in terms of rows instead of individual elements, then everything would have been so much cleaner. That's what's going on here. Okay? So, how do we derive these? Well, we start with the post condition. Okay? We start by thinking, okay, what is it that we want to compute? We recognize that we invariably want to march through the matrices in a consistent fashion. Sometimes this is from left to right. In this particular case, we know from, we actually know from experience when there are triangular matrices involved that it's convenient to go from top left to bottom right because that exposes these nice blocks of zeros in the triangular matrices. Okay? So, we partition A, L, and U into quadrants. And then we say, okay, when we're at some step in the loop, we would like to reason about what is in these quadrants. It would be beneficial to understand how those quadrants are completely updated when we're completely done. Because inherently, when we're in the loop, we're not completely done yet, so therefore it is a subset of the operations that need to be done that are done. All right? So what you do is you take these partition matrices, and all I've done here is I have plugged the partition matrices into the post condition. Okay? So every time there's an A, I've replaced it by the 2x2 matrix that represents A. Same thing for L, U, etc. You with me? Then we do what we often do. So the first thing we do is what we often do, which is partition. The second thing we're going to do is say, okay, once we have partitioned matrices, let's just multiply it all out. So going from here to here, all we've done is multiplied out the left-hand side so that we get explicitly what must be in the different quadrants, and then we've set that equal to the original contents of A. And that gives us a bunch of expressions of what must be true about the different quadrants of L and U. And if you look at this very carefully, what you actually see is a recursive definition of LU factorization. Now you might then say, oh, we should use functional programming where recursion is so natural, etc., etc. The problem is that we like to always use a loop because we're going to see when we look at blocked algorithms that we want to march through the matrix in blocks that respect the cache sizes because that's what allows us to achieve high performance. So recursion is just not it for us. All right, so we go on. So we call this the partitioned matrix expression. So think of the partitioned matrix expression as the recursive definition of the operation that we're trying to implement. Okay? That expresses in terms of the different quadrants what must be in A when we're completely done. Okay? If we started our loop with that in A, then we wouldn't have to do anything in our loop because we'd already be done. Obviously, it would mean we would have to do something before we enter the loop, so that's not particularly exciting, but you get the point. Okay? So, now, a loop invariant, I would then say, is okay, instead of expressing everything that must be done, something is not yet done because we're still having to execute the loop to get finished. Okay? So what you do is you look at your partition matrix expression and you indicate that something is not quite done. Now, if you look very carefully up there, when we're completely finished, the bottom right corner must be updated with the LU factorization of the updated matrix. And what we're saying here is if you look at the bottom right quadrant of the second expression there, we say, look, if we haven't yet computed the LU factorization of that quadrant, then in A, we may want to have the original contents of A minus the bottom left part of L times the top right part of U. That's what's given here. And as a result, we don't actually need this equality in our reason. So what you learn from this is you say, look, something has not yet been done. The final step of computing the LU factorization of the bottom right part after it's been updated has not yet been done, but I have updated the bottom right part up to that point. Okay? If you think about it, that's exactly the condition that we maintain in the LU factorization algorithm that we came up with last time. Okay? Because we're done with these parts, and we now only need to do an LU factorization of what's left. You with me? But we're coming up with this a priori. Huh? Pretend that you didn't know that algorithm yet. It turns out that that way you can actually come up with 5 different states to maintain. Why only 5? Because there are certain operations that inherently must happen before other operations. Okay? You can't really assume that this has been satisfied or that this has been computed if you hadn't yet computed L top left, etc. Or rather, if you did that, that'd be kind of dumb because you took something that you'd computed and you threw it away. Now you're going to have to recompute it again in the future. Okay, so there's the partition matrix expression. And one algorithm that you could come up with is to say, look, the top left part we've computed the LU factorization of, and we've overwritten that part of A with it, but the other parts of A we haven't yet done anything with. Okay? In the literature, sometimes that's called the bordered algorithm. And actually, that particular algorithm is great if you're trying to prove that the LU factorization without pivoting completes if and only if the leading principal submatrices are themselves not singular. Okay? That's actually the one you want to use. But that's not what I do in the notes, so oh well. Here's one that's known as the left-looking algorithm. And the idea is that everything to the left of this bar has already been computed, and nothing to the right of that bar has yet been computed. And it turns out that if you do out-of-core computations, if your problem is so big that you must store the matrix on disk, this particular algorithm turns out to be very convenient. Why? Because as part of the computation, you compute a next slice of the matrix, which is relatively little data. You update that while it's in core, and then you can write it out to main memory. And if along the way a fault happens, your disk, well, not your disk fails, but your processor fails, then it's actually really easy to checkpoint and restart, which is a way of providing fault tolerance in your computation. So that algorithm actually has practical implications. Then there's sort of the mirror part of, this one doesn't fit so well, of the left-looking algorithm, and this could be called the up-looking algorithm. So everything above this bar is finished, nothing below it has been touched yet. This is probably the one algorithm that is not particularly useful. This one turns out, we probably won't get to it today, this is known as the Kraut variant, and this one turns out to be the easiest algorithm for which to prove backward stability of LU factorization. So I'll use this. Actually, in the notes that I'm going to post, we use this example to show the backward error analysis of LU factorization. And what you will see in those notes is that we, just like here, we do a goal-oriented derivation of the algorithm, there we do a goal-oriented derivation of the backward error analysis, which is why I'm going over these slides, is so that you understand better how that particular paper fits into the big picture. And then finally, there is the one for which we already have an algorithm, which is sometimes called classical LU. Okay? And so, if you go back in literature, you find that all 5 of these algorithms at one point in time were discovered over the course of more than 100 years, I think almost 200 years. And essentially with this formal derivation methodology, you can derive all of them. Well, if you get to be as good at it as I am, I can do it and typeset it in LaTeX probably, in about 30 minutes. Okay? Which of course is dumb because we have this automated system to do it, so why do I do it by hand? Well, I don't know, I just like doing it. So, once you have a bunch of candidates of what you may wish to maintain in the matrix, you pick one of them and you derive the algorithm associated with that loop invariant. So what we're going to do is we're going to pick the variant, the loop invariant that's going to lead to the exact algorithm that we saw before. Okay, just so that you have something to relate back to as we discuss this. So how does this work? Well, it turns out, this is again, notice that red is always what we just filled in the worksheet. And it's always hard to see because of the size of it, right? I should have handed out hard copies of this so you could have stared at it. So let's zoom in on it a little bit. Now, all I have done is said, look, what we would like to do is have it be so that the loop invariant is true before the loop starts. That's the base case of for the principle for the proof by mathematical induction. Okay. Now notice that absolutely nothing happens between where it's true before the loop starts and the top of the loop because there's no computation happening in between. Okay, so the first time into the loop it's going to be true there. If we can then prove that it's again true at the bottom of the loop, now it's true at the bottom of the loop for a matrix where that thick line has moved a little bit. Okay, we've sliced through the matrix a little more. Then it's true that if we go back to the top of the loop and we end up back right up there, it's still going to be true because no computation happens between here and there. Therefore, every time through the loop, it's going to be true. At some point, we're going to drop out the loop, and actually, we shouldn't have had the loop guard in there yet because we don't know the condition for which we actually drop out. We're going to derive that. What that means is that right here it's true because no computation happens between here, recognizing that we're done, and coming out of the loop. If we can then prove that A being in this state implies that we have computed exactly this, then we know that the algorithm is correct. Of course, correct in exact arithmetic, not necessarily in the presence of round number. You with me? Okay, so notice that the precondition and the postcondition, and knowing how we're going to march through the matrices, have given us a loop invariant. And now what we're going to do is determine what this loop guard must be. Under what condition should we come out of the loop? Okay? Now what do we know? We know that we want it to be that the loop invariant is true when we come out of the loop. And we want it to be that the loop guard is false when we come out of the loop. This is the logical AND. We want to now pick this condition that takes us out of the loop so that this implies that. Now, under what condition does this imply that? If A top left is in the entire matrix A, then this is just that. if L and U top left are just L and U, then that gives us that. And then these conditions go away, and we get exactly that. Okay, so the condition for coming out of the loop is that we've reached the end of the matrix. The condition that keeps us in the loop is that we have not yet reached the end of the loop. Fair enough? So with that, we determined that the row dimension of A top left being less than the row dimension of A is what keeps us in the loop. Of course, that means that we're making an assumption about A being square, which actually is a little dangerous because sometimes we do this algorithm on a non-square matrix, but let's not get into that. You with me? But the important thing is that the loop invariant together with the post condition dictated the loop guard. Loop guard is not unique, but we pick one. You with me? This is very computer sciencey, isn't it? Ooh. It's a good training of the mind. It's how you should think about it. Yes?
I think the reason that we're saying M not M A top left less than M A is because of that's the exact inverse of this invariant, but in reality this is
The inverse of the loop guards.
right. But in reality it's actually the main point, right?
There are lots of ways of expressing that. You're hitting on the minor. So we really want these to be equal. We recognize that A top left can never be larger. Therefore, saying that it's not less than means that it's equal is part of the reason that it's so yeah. But you're hitting upon a slight subtlety that indeed is a little sloppy. Good. Okay, you with me? Pretty bizarre. So, where in this whole thing do we fill that in? Well, we fill it in as the loop guard there, but it also knows that when we pass that guard, we know that the top left is not yet all of A. You got it? So we fill that in the worksheet, and we go on. Next, we look at initialization. Okay, so let's look all the way at the top. We know that we come in with A being equal to the original contents of A. We would like to partition our matrices A, L, and U in such a way that we end up making the loop invariant true. Now, how can we partition our matrices in such a way that our loop invariant is true? Okay, well, this is a little subtle because it means you have to understand what arithmetic with empty matrices means. So let me just sort of give it away. We know we better partition the matrices, otherwise we don't even know what these expressions mean, right? But then, if you take A top left to be empty, and the same for L and U, then subtracting off L bottom left times U top right gives you the zero matrix. So you get the original contents A hat bottom right, but that's all of matrix A. And actually you have no further constraint on it because the three parts that do have the qualities there disappear because they're empty. Okay. So, simply partitioning the matrices in such a way that the top left quadrants are empty, which is what we saw we had to do before anyway, puts you in a state where the loop invariant is true. So if I asked you, prove this by induction, you would say, oh, I can now prove the base case is true. But what's important here is that the precondition together with the loop invariant that we chose dictate how the matrices should be partitioned. That's the real insight. And notice that I use things like prescribe, dictate, okay? You have no choice. What must be true in a certain point tells you what operation must be performed. Okay, so now we have that in our loop in our thing, and now we get to the actual loop body. Well, we need to move through the matrices. We need to make progress towards completion. So for that, we know that we need to take our matrices, repartition them to exposed submatrices, and then at the bottom of the loop, move our thick line forward. Okay, that's something that you've seen before. So we can put that into our worksheet. We got it like there. Now we're getting somewhere. Now here comes the trick. We know, I really should have a pointer. We know that the loop invariant is true right there below the while loop, right? We know that we're repartitioning the matrices, but notice that repartitioning the matrices is just an indexing step. There's no computation happening there. Therefore, in this next gray box, with the letter 6 next to it, we know that the loop invariant is still true, but we can now express that loop invariant in terms of the submatrices that we're exposing. And that tells us what is in those submatrices. Okay, so how do we do that? We take our loop invariant, we look at how we repartition. Oops. Okay, so there's our loop invariant. And then we simply take what is a top left, what is a top right, etc., and we fill that in the loop invariant. That's what in computer science we would call a textual substitution. It's mechanical. And then we do some arithmetic, or linear algebra, and this tells us exactly how the different parts of the matrix have been updated so far by the loop, if we are maintaining the loop invariant. So the fact that we're maintaining the loop invariant dictates that this must be in the matrix. It's mechanical. It's a matter of pushing through symbols and applying linear algebra. Okay, so you take that and you fill it in your worksheet. Right there. Then you go to the bottom and you say, I must be in this state again when I'm done. I have now redefined what the different regions of my matrices are. So let's take those and simply plug in what a top left becomes by the time you reach the bottom of the loop. Okay? Again, that's textual substitution followed by some linear algebra to express what must be in the different regions of the matrix at this point. Boy, the other derivations are starting to look awfully simple, isn't it? It's very mechanical. It's just a matter of pushing through the symbols. You take that and you plop it into where it needs to be true in your worksheet. I keep losing that. And now we have our entire proof of correctness there, except that we have yet to determine how the matrix must actually be updated by the loop. Okay? But what do we know? We know that we must be in this state at the bottom of the loop. We know that we are in that state at the top of the loop. And what we need to do is we need to figure out what to update. Well, notice that A00 must have, oops, there's a typo there, L and U00 in it, where L00 and U00 must satisfy that. But if you look up there, A00 already has that in it, modulo that typo. Okay? Good. Nothing needs to be done there. Similarly, you can conclude that this, and that part of the matrix already is in its final state. Nothing needs to be done. Unless I have more typos. No, I think that's all right. So let's focus on alpha 1, 1. If you go to the top of the loop, alpha 1, 1 has the original contents, which is again a typo, there's a 1, 1 missing there, minus the inner product of the part of L and U in it. It must have upsilon 1, 1 in it. That means we have to somehow compute upsilon 1, 1. But if you go over here, upsilon 1, 1 must be equal to alpha 1, 1 hat minus that. So, alpha 1, 1 already has that in it. Nothing needs to happen. No update needs to occur. You with me? Now, The same thing goes here. You can argue that this already contains that and therefore nothing needs to happen. If we now look here, we want L21 to be there. We have that expression already in that variable. L21 is related to this minus that by having to divide by epsilon 11. We know that epsilon 11 is currently in alpha 11. Therefore, all we need to do is take the current contents of A21 and divide it by alpha 11 to update it to what it needs to have. Getting the hang of it? So you do that for all the different parts of the matrix. And you conclude that these are the updates that must happen, which are exactly the updates that we saw before. And what we've just done is very systematically derived the exact same algorithm as we had before, except that when we then plug it into this worksheet, we have the proof of correctness sitting there as well. Nobody can doubt that this is going to give the right answer. As a matter of fact, we don't even need to implement it, right? It's correct. And then what do? You throw away all of the parts of this worksheet that have to do with the proof of correctness, and you're left with the algorithm that we saw before. And that's goal-oriented programming. You derive the algorithm to be correct hand in hand with its proof of correctness, which for a loop-based algorithm is approved by induction. Yes?
For all of the other algorithms we looked at in this course, can they be derived in the same method?
Every algorithm we have seen so far in this course can be derived this way, yes. Okay? Even the algorithm for computing the singular value decomposition, except that there is a step in the algorithm that itself is very complex. So essentially we're sort of saying, well, when you run into complexity, hide it in a subroutine. Let's assume we have a magic routine that gives us this, and then we can have the algorithm. Okay? And you can sort of see how the proof of the existence of the singular value decomposition then fits exactly into the worksheet. Okay? And as a matter of fact, one observation is that you could take an algorithm like this, and if you want to prove something about the algorithm, you can use the algorithm and the worksheet as a framework for that proof of whatever property you are trying to prove. For example, backward stability. Okay? Which is what's done in one of the papers I'm going to hand out. And I'm sort of going to lead you through it as part of a simpler algorithm as part of the exam. Okay? Okay. Now this could, of course, be just a computer scientist trying to justify the existence of computer science as a science. But the fact is that this is really, really cool stuff. Okay? We have applied this to operations for which people were still writing journal papers where essentially every time they came up with a new algorithm, they would get another journal paper out of this. And we essentially sat down in one afternoon and derived 56 different algorithms, all of which outperformed theirs. Okay? So, this is powerful. This is really powerful. Now, what you then notice, of course, is now we have a proof of correctness for this algorithm that's now typeset in this very nice way. But if we then code it in the traditional way, there would be plenty of opportunity to introduce bugs in translating this to the intricate loops that you would have to implement this. Which is why we introduced this API for programming these algorithms, because then you can't make a mistake in translating the algorithm into the actual code, and therefore the correctness of the algorithm carries through to the correctness of the code. All right? So that's part of the whole philosophy behind essentially this project that I lead here at the University of Texas, where 15 years ago we did a lot of this kind of foundational work that was more theoretical, And over time, as part of showing that this actually has practical implications, we have then also created a whole new linear algebra software stack that builds on these ideas. Okay. Good. So then you repeat for all of the other loop invariants, and you can come up with other algorithms. And in the notes, I don't actually walk you through the derivation for all of the other ones using the worksheet, but if you look at the notes and the way I present it, you can recognize the worksheet. Okay, so let's have a look at that. Open. Why is my computer always so slow? Okay. If we go to LU and we look at the notes, at some point, I'll blow this up a little bit. Just let's get to it. So, deriving algorithms for triangular systems follows exactly this way. It turns out that Gram-Schmidt versus modified Gram-Schmidt is literally a matter of picking a different loop invariant. Deriving householder QR is tricky. As a matter of fact, there it's all about formulating the post condition just right, and then everything falls in place. But it took me a month to figure out how to formulate the post condition right so that it all fell out. Okay, so, and that one actually I don't think I've written up anywhere. But here is how I do it in the notes. I do show the different loop invariants. But then instead of showing the, I can't go to the next, here we go. So let's focus on the crowd variant because it's going to become important in further discussion. Up there is the loop invariant. I then say at the top of the loop, A contains that. That's simply the loop invariant, but with the repartitioned matrices and then filled in. Okay? And at the bottom of the loop, we would like for it to contain this. So what's happening with the crowd variant? You're completely done, except that the bottom right part has not been touched at all. And what we're trying to do is compute one more row and column of the result, where the parts in blue are not yet computed. And then if you take your the constraint on how A is related to L times U, and you multiply it all out for a partitioned matrix that exposes all of these submatrices, you get all of these expressions. And then it turns out that you can use these equations right here to determine exactly what the update must be, because what's in red you already know because it's part of what has been computed at the top of the loop, and what's in blue, which is a little harder to see here, is what you would like to compute. And essentially, you solve those equations for what you need. Okay? And so let's look at the crowd variant in a little bit more detail. What isn't A is this. have computed L and U. But this part has been left completely alone. Okay? And you know that the top left part of A must be equal to L top left times U top left, the original content. You know that the bottom right left part has to be equal to L bottom left times U top left, like that. And you know that A top right, the original contents, was equal to L top left times U top right. Okay? If you then repartition, you get to this point right here. And what would you like? Well, you know that at this point, this has already been updated with its factorization. This has already been updated with its part of L. This has already been updated with its part of L. This has been updated with its part of U. Why? Because these parts are already done. But at this point, this is still original. How does that fit in with the worksheet? You're at the top of the loop. This is true. You're now indicating what is true after you expose the submatrices. Okay? So this part here is what we want to work with. Now, we would like to update this with epsilon 1, 1, this with U1, 2 transpose, and this with L2, 1, because then we can move forward. Okay? How do you determine what that needs to be? Well, if you take your partition L, let's see, there's a 1 here, L2, 1, L2, 2. And you multiply that times U. If you look at, you know that has to be the original contents of A. Let's just focus on the ones that we need, because I'm getting tired of writing. Okay. Notice that this is equal to this times that plus this times that plus 0 times that. Okay? That gives you this equation right here. But notice that we already know what this is and what that is, and we can find those right there. Okay? So what does that mean? In this equation, this is known because it's currently in alpha 1, 1, and these are known because they are in their respective parts of A, and therefore we can compute that. Once we know that, we know this, we know that, we know that, and we know that, we can compute that. Okay, and notice that we need to take this, subtract off a matrix vector multiply, and then divide by an element. And here, what we need to do is take a row vector, subtract off a row vector times a matrix. That's, of course, just the transpose of a matrix vector multiply. And then we have that. And then we've computed what we need, and we can move on. Okay? Notice that what that involves is a dot product. We know something about the backward error analysis of dot products. A matrix vector multiply. We know something about the backward error analysis of that. Or a lot of the error analysis. A divide, that's part of our standard or our modified computational model. And then here again, it's just a multiply. So we have the bits and pieces of the error analysis that might be needed in order to prove something about the numerical stability of all of this. Which is why this is the one that's easier to choose for performing the error analysis. Okay? All right. What we could do now is we could move ahead and look at the backward stability result for L factorization. But that perhaps I've already burdened you with quite a bit. Plus, I suspect that doing the exercise that I have planned for the midterm will get everything fresh in your mind for Tuesday, and therefore maybe we should delay that until Tuesday. Okay? I'll tell you what the result is. The result turns out to be slightly different from what I claimed before. Okay. My computer just froze. Oh wait, here we go. Oh well, we'll see it on Tuesday.